Hello, my dear ones. How are you? I'm back to complete the pedigree analysis. This time we're supposed to know how can we know the genotypes and how can we calculate the risk using a pedigree. First of all, how shall we write the genotypes? In the case of autosomal recessive diseases, so if the disease we're studying is recessive and it is autosomal, carried by an autosomal chromosome. In this case, the symbols are going to be capital letter for the normal dominant allele and the lowercase or the small letter for the diseased recessive allele. In the case we have a diseased individual, then the genotype in this case is supposed to be pure. Pure, small d, since the individual is diseased. So this is if we can notice that the individual is diseased from the pedigree and the diseased allele is recessive. So we already know that the diseased allele is recessive. So it is necessarily pure. Also, we can say instead of pure homozygous in the genotype for it to be expressed into the phenotype. So this is how we are supposed to write the genotype of an individual who is diseased in the case where the diseased allele is recessive. In the case where there is a normal individual, the genotype in this case is supposed to be either capital N or capital N small d. يعني the genotype is supposed to be either pure or hybrid. The justification is since the individual is phenotypically normal, this is clearly because we can notice that he's normal from the pedigree, he or she is normal from the pedigree, then we have to write that this individual is phenotypically normal, and since the normal allele is dominant, so it can be present in pure or in hybrid form in the genotype, and in both cases it is going to be expressed into the phenotype. Now, in the case of autosomal dominant diseases, so in this case, if the disease is dominant, of course, the symbols are going to differ. We're going to symbolize the diseased dominant allele with a capital D and small n for the normal recessive allele. The genotype in this case of the normal individual is supposed to be small n because the individual is phenotypically normal and the normal allele is recessive, so it shall be present in the pure form in the genotype for it to be expressed into the phenotype. Or else, because if this recessive allele is present with the dominant allele, then the dominant allele is gonna mask it. So the only way for a recessive allele to be expressed to the phenotype is that being available or present in the pure form in the genotype. Genotype of a diseased individual is going to be either capital D or capital D small n, since this individual is phenotypically diseased and the diseased allele is the dominant one, so it's always expressed to the phenotype whether it is in the pure or hybrid form in the genotype. In case of gonosomal recessive diseases, so the cases we were discussing are in the cases of the autosomal diseases. Now we are going to check out how are we supposed to write the genotypes in case the disease was recessive but gonosomal. First case, if the gene responsible for the disease is located on the non-homologous segment of chromosome X. The symbols are going to be capital N for the normal dominant allele, small d for the diseased recessive allele. The genotype in this case is going to differ between a male and a female, and this is because the male's gonosomes or sex chromosomes are XY, while that of the female are XX. So, if we have in a pedigree a diseased female, then the genotype is going to be XD. Why? Or what's the justification for such a genotype? We're supposed to say because she is apparently diseased. This is what we noticed from the pedigree. And we already have confirmed that the diseased allele is recessive, so it shall be present in the pure form in the genotype for it to be expressed into the phenotype. In the case where the diseased individual is male, remember that we're discussing the location of the chromosome, that it is on the non-homologous segment of chromosome X. In this case, the male has only one X chromosome, so since he is diseased, then the diseased allele will be carried by this one X chromosome that he possesses. So his genotype is gonna be XDY. This is because he is phenotypically diseased and the diseased allele is present on the non-homologous segment of chromosome X. This is why his genotype is gonna be XDY. In the case where the female appears to be normal and the diseased allele is present on the non-homologous, or the gene we are studying is present on the non-homologous segment of chromosome X, then the genotype of this female is going to be XNXN or XNXD. This is because she's phenotypically normal. The normal allele is the dominant one, so it is going to be expressed to the phenotype whether it is pure or hybrid in the genotype. As for a normal male, then the genotype of a normal male will be XNY. This is because he appears to be normal and the gene is located on the non-homologous segment of chromosome X. Then there is he's going to express this allele, and whatever the phenotype that he possesses is going to reveal clearly his genotype. Okay, so in the case where the disease was dominant, you apply the same way, but taking into consideration that the diseased allele is going to be capital D and the normal one is going to be small n, and you apply the same procedure. As for the gonosomal dominant diseases, if the gene responsible for the disease now is located on the non-homologous segment of chromosome X, so this is our second case in the gonosomal diseases. In this case, we have chosen the dominant disease. The diseased allele, capital D, is going to be the symbol of the diseased dominant allele, and small n for the normal recessive allele. The genotype of a normal female is obviously going to be X small n because she's normal and the normal allele is recessive, so it's supposed to be pure in the genotype to be expressed to the phenotype. The normal male's genotype is going to be XNY. Again, this is because he appears to be normal, the normal allele is recessive, and this allele is present on the non-homologous segment of chromosome X. He only has one chromosome X, so this chromosome X will carry the allele that appears to the phenotype. The genotype of a diseased female is going to be either XDXD or XDXN. Again, this is because she's phenotypically diseased. The diseased allele is the dominant one, which can be expressed to the phenotype, whether it is in the genotype in pure or hybrid form, while the genotype of a diseased male is necessarily going to be XDY because he is phenotypically diseased, the gene located on the non-homologous segment of X, so he is going to express it into his genotype. If the gene responsible for the disease is located on the homologous segment of chromosome X and Y, remember that we said that the chromosome that the male chromosomes or sex chromosomes, gonosomes X and Y, are non-homologous. They do not have the same size. There is a part of X which is not homologous to Y, a part of Y which is not homologous to X, and a part of X and Y that are homologous. These parts usually they act as if they are autosomal, so they have to be present in two copies, in the male and in the female. With respect to the recessive diseases, in the case where the normal allele is dominant and the recessive one is for the diseased allele, the genotype of the diseased female is going to be XDXD because this female is diseased, the diseased allele is recessive, so it is necessarily homozygote. As for the genotype of a diseased male, remember this time we're discussing the localization of the gene which is on the homologous segment of X and Y. So in this case we are also supposed to put the allele on the Y chromosome. So because he is diseased and the diseased allele is recessive, he is going to carry the recessive allele on both his chromosomes X and Y. So his genotype is going to be XD-YD. This is because he is phenotypically diseased and the diseased allele is present on the homologous segments of chromosome X and Y. If the gene responsible for the disease, we're still in the same case, is on the non-homologous segment now of chromosome Y. In this case, of course, no females are going to be affected because females do not have any Y chromosome. For a recessive disease, the genotype of a diseased male is going to be XYD. So because we're discussing here the non-homologous segment of chromosome Y, so we're not supposed to put any allele on chromosome X. It's not the carrier of this gene that's under the study. So in case the male appears to be diseased, then his genotype is clearly going to be XYD, and the genotype of a normal male is going to be XYN. For a dominant disease, the genotype of a diseased male is going to be XY, and this time the dominant allele is the capitalized one. It is the diseased. This is why we are going to place it capitalized. And for a normal male, it is going to be Y small n. Let me get back to the previous slide because I think I might have skipped something. Okay, no. Okay, now regarding the risk calculation. Calculation of genetic risk of a couple to have an affected child. So how can we calculate the risk for a particular couple to have an affected child? First of all, we're supposed to be, the cases that we are going to study are for autosomal recessive diseases. You're supposed to know this rule, that to calculate the risk, you can use this rule, or if you are very sure of the genotype of both parents, you can apply the table of Cross to check out what is the risk for this couple to have an affected individual. As for our rule that you're supposed to know, the risk for a couple to have an affected individual is the probability of the father to be hybrid. And in case he was hybrid, what is the probability for this father to give the affected allele times probability of the mother to be hybrid times probability of the mother to give the affected allele. So this is the rule that you're supposed to know in the calculation of the genetic risk. First case, given that in this case it's given that the probability for an individual in a population to be hybrid is 1/3. It's this given is for this particular disease. In other diseases, this probability will be given to you, and it might be, of course, different than 1/30. Our pedigree here shows a female married this male, and they're expecting a child. This is the fetus, and we're supposed to calculate the risk that this fetus might carry a certain disease, that in a population where in the case where the family history of each of the parent is not known, then we consider that he or she is hybrid for this disease. Then we have to consider that probability for him or her to be hybrid for this disease is 1/30. So we're supposed to apply the rule that we mentioned before. In this case, because both of the parents are of an unknown family history, then the probability for each one of them to be heterozygote or hybrid is 1/30. This is given to us. In case they were hybrids, the probability for each parent to give the affected allele is definitely 1/2, because if the genotype of the parents is ND, let's suppose, then there is 1/2 probability that they will give their children the allele which is the normal one, and 1/2 or half or 50% probability that they are going to give their children the allele which is carrying the disease. This is why we say 1/2. So the risk in this case, remember that the risk is the probability for the father to be hybrid. In this case, it is 1/30, times in case he was hybrid, probability to give the affected allele, which is 1/2, times probability of the mother, since she is also of an unknown family history, then we have to use the same proportion, which is 1/30, times probability to give the affected allele, which is 1/2. So in this case, the risk for this couple to have an affected child is 1/3600. Second case, as you can see in this pedigree, we are still with two parents of an unknown family history. they're expecting a child. We want to know or calculate the risk that this child is going to be affected. And as you can clearly see, they already have an affected child. So this is our pedigree. In this case, both parents appear to be phenotypically normal. So of course their genotype is supposed to be N, but because they have already an affected child, so this affected child has inherited the D allele from each one of them, so their genotype is definitely ND. So this means that they are 100% hybrids. This is why we're supposed to put the probability for the father to be hybrid 1, which is 100%. Probability for the mother to be hybrid is also 1. Then the probability for each one of them to give the affected allele is 1 over 2. So the risk in this case is 1 for the probability of the father to be hybrid, half for the probability to give the affected allele, times 1 for the probability of the mother to be hybrid, because she is hybrid for sure, times half for the probability to give the affected allele. So in this case, the risk is 1 over 4. Again, I will remind you that you can use the table of cross, because in this case you are very sure of the genotypes of both parents, which is ND for each. So in this case, if you apply the table of cross, you will reach the result of 1 over 4 for this fetus to inherit the D allele from each one of these two parents, and you will reach the same result. Third case. In this case, this is the couple expecting a child and wondering if their child is gonna suffer from the disease, especially that the mother in this case has a diseased brother. So as you can see, the father is of an unknown family history. So this is our pedigree. The probability for the father to be hybrid is of course 1 over 30, because we do not know his family history, and it's given to us that when we do not know the family history, then we use the probability to be hybrid 1 over 30. The probability of the mother to be hybrid in this case, every time you notice that the mother has a diseased brother or sister, then you directly put the probability for her to be hybrid 2 over 3. Let's see why. If you take into consideration her parents are definitely hybrids. The genotype of both parents is ND. This is because they have an affected child. So, the mother will give the gametes N and D. The father will give the gametes N and D. Every child born will have a probability to have a genotype of NN, ND, or DD. Now, remember that our rule is the probability or the risk. To calculate the risk, it is equal the probability for the mother to be hybrid. As you can see here, she appears to be normal. This is why I crossed this result, because she's not diseased, so I cannot consider this result because she's apparently normal. So I am left with the 3 results, and this is why I placed 1 over 3 for each one of these results. Now we have 1 over 3 possibility that the mother will be having a pure genotype of NN, 1 over 3 probability that the mother will have a hybrid genotype ND, and another 1 over 3 to have a hybrid genotype of 1 over 3, which means that the risk for the mother to be hybrid in this case is 2 over 3, and this is why we used 2 over 3. So this is the justification of why we have chosen 2 over 3 for the mother to be hybrid, since she is already having an affected brother. In this case, of course, the probability for each parent to give the affected allele is 1 over 2. So the risk is 1 over 30 because the father is of unknown family history, times 1 over 2 to give the affected allele from the father, times 2 over 3 for the mother to be hybrid since she already has an affected brother, times 1 over 2 to give the affected allele, and this is gonna give us a risk for this couple to have an affected child 1 over 180. Fourth case. This is a case in which both parents appear to have a diseased brother. So in this case, the probability is supposed to be 2 over 3 for both of them to be hybrids, since they both have affected brothers, times the probability to give the affected allele for both of them to be 1 over 2. This is how we calculate the risk, and it is going to give us a result of 1 over 9 for this couple to have an affected child. Case number 5. As you can see here, we have two parents of an unknown family history, but the father is already affected. For the mother, you are going to use the probability given to you, which is 1 over 30, since we're not sure of her family history. So for the mother to be hybrid, it is 1 over 30 because her family history is unknown. The probability of the father to be hybrid, he is obviously not hybrid. His genotype is definitely small d, small d. But we cannot put 0. Yani the probability for the father to be hybrid is null. It's obviously null because his genotype is well known, which is DD, since he's already affected. So in this case, we are going to put the probability as 1. Probability of the mother to give the affected allele is 1 over 2. However, the probability for the father to give the affected allele, remember that his genotype is small d, small d. So the only allele that he will give to his children is the small d. So we are going to put the probability for the father to give the affected allele, the small allele or the affected allele, it is 100%, which is 1 in this case. So the risk is 1 over 30 for the mother to be hybrid times 1 over 2 for the mother to give the affected allele times 1 for the father to be to give the affected allele, because he will surely give the affected allele. This will give us a risk for this couple to have an affected child of 1 over 60. Last case, the father in this case is already affected. The mother is normal, however, her brother is affected. So the probability of the father to be hybrid, in this case the probability for him to be hybrid is null, so we are going to place 1 because we cannot put 0, or in this case the risk is going to be 0, and this is not correct. So it is 1. He will definitely give the affected allele, so the probability for the father to give the affected allele is 100%, which is 1. Probability of the mother to be hybrid, since she already has an affected affected the brother, then we are going to put her probability to be hybrid 2 over 3 and 1 over 2 probability to give the affected allele. In this case, we are going to multiply the 1 coming from the father with the 2 over 3 times the 1 over 2 coming from the mother, which will give us a very high risk of 1 over 3 for this couple to have an affected child. You have to note that if you know the genotypes, this is something I already told you, of both parents, you can determine the risk by using the table of cross, and it's always applicable that you apply the rule we've been discussing, of course. If the disease is dominant, because we were discussing in all our cases a recessive disease, if the disease is dominant, you simply find the risk for the couple to have a normal child instead. When you calculate the risk by using any of the cases, by using the rule applied on any of the cases that we mentioned, then you have to subtract the result that you obtained from 1. So 1 minus the result will lead you to know the risk for this couple to have a diseased child. Or also, if you know the genotypes and you are very sure about them, you can simply use the table of cross. Because in all these cases we were discussing autosomal diseases. In the case of gonosomal cases, usually males are going to be of known genotypes. So the genotype usually of the gonosomal diseases, usually the genotypes of the males are very well known. Okay, so in this case you find the risk for the female to carry and transmit the affected allele, and this is gonna give you the risk for this couple to have an affected child. Thank you very much. I hope that this video was fruitful and you benefited from it. If you have any question, I'm always ready. Bye.